Hello, everyone. We are presenting on piezoelectric window films and sound attenuation. My name is Lily McCalmont.
I'm Daniel.
Hi, I'm Ted.
And I'm Jeff.
Justin.
So to start us out, I'm going to talk a little bit about the current sound attenuation or soundproofing materials that currently dominate the market. Most of them are bulky foams, padding, really anything that could impede sound by simple absorption, as shown on the left here in this diagram. The methods really just depend on physically absorbing or diffusing the sound. However, there is another method called active sound attenuation because this actually has the capability to receive an input of incoming noise and then output its own waves that will diminish the sound through destructive interference. You can see this diagram on the bottom right here depicting the system that we aim to replicate in this project. You have one film sandwiched between two planes of glass, allowing enough room in between for the film to wiggle and generate the necessary waves. Excuse me. So our goal is to develop a window film that is capable of actively attenuating noise. This has many possible applications in work environments, recording studios, homes, especially noisy, population-dense areas where sound pollution is a real problem. I'm not going to get too much into it in this presentation, but there is a growing market for soundproofing materials as shown in this graph right here. And right now, there is no other current product on the market. Active sound attenuation has been applied to headphones and electronics, but never to structures such as walls or windows. So we hypothesize that we will be able to develop this system using a piezoelectric film when voltage is applied via the piezoelectric effect. For our design specs, we want to try to attenuate at least 5 decibels of noise for our preliminary experiments. We want our film to be at least 75% transparent for window applications. And then we also need a material that has a high D33 piezoelectric constant to demonstrate that effect. So to select our material, we examined various different properties that fit our purpose, taking into consideration not only its technical performance, but as well as its feasibility and toxicity, because this will be in people's homes and offices. In the end, we selected polyvinylidene fluoride, abbreviated to PVDF. This is a transparent piezoelectric film. So with that, we're kind of going to dive deeper into the details of our project. We have 2 main parts. First is a materials characterization analysis, which examines 2 different phases of PVDF, and the second is our actual experimental design and results.
So the first method that we're going to discuss that we did for characterization is optical profilometry. So the way optical profilometry works is that it uses reflected light. One beam hits the sample, one beam hits a very flat reference mirror. So the path difference would be caused by any irregularities in the surface of the sample that we're hitting. So what these images are showing you are the 2 samples that we had. So there are 2 samples of PVDF that are significant in our project. Alpha phase, which is any raw PVDF that you would find on the market. It's non-piezoelectric. Sample B is beta phase, which is a crystalline polymorph of PVDF, and it is piezoelectric. And we'll get into the details of why the surfaces look different. So sample A, like I said, is alpha phase, and from our images that were generated from the testing, we got a roughness average value of 2.5 microns. We can see from the images that there's a large amount of anisotropy on the surface, very few regions of flat topography. The beta phase, sample B, sample that we tested, had a roughness average value of 0.35 microns. It's much more uniform on the surface, much flatter topography. And the reason for this is that sample B has been stretched and polarized under tension. This is what makes it piezoelectric, and it changes the crystalline polymorph from alpha phase to beta phase, which is much more organized. So this is showing the difference between alpha phase and beta phase. You can see that in beta phase, the fluorine and the hydrogen atoms are oriented in the same way consistently throughout the whole polymer chain, whereas alpha phase, they're just kind of randomly organized. So we would expect to see a much higher degree of uniformity and less roughness in the beta phase sample, which we did confirm that with our results.
In order to prove the higher order of the crystalline structure, we wanted to use X-ray diffraction to compare the alpha phase and the beta phase. So on our left is our alpha phase. We can see that's 32% crystalline. We see a lot of broad peaks. In comparison, the beta phase has a lot fewer peaks that are wider than 2 degrees. So it is more crystalline. So in addition, we wanted to deposit indium tin oxide to make a transparent electrode. So indium tin oxide is the most common transparent conductive oxide. So it both conducts electricity and it's additionally transparent. So it's great for window applications. In addition, we wanted to do ellipsometry to evaluate if our sample was sufficiently transparent and to verify the thickness of our deposition. So here we can see our results from our ellipsometry. We see our percent transmission as a function of wavelength. The curve we want to pay attention to is the red curve with PVDF with ITO coded on both sides. And we want to compare that to the green curve with uncoded PVDF. We see the median value for our coded PVDF is 51%. And when we compare that to our green uncoded curve, we see a loss of 15% transparency.
So to kick off our experimental design, we want to show you the environment that we designed to test our experiment. You can see here the prototype we initially developed with a sample holder on one end and a full range speaker mounted on the other end. This is a more in-depth look at how we actually tested the film. On the left, you can see our prototype housed within 2 sound isolation boxes that we made to isolate the experiment from outside sound. In the upper right, you can see the amplified circuit that we built to drive the film. It consists of a small mono amplifier and a 10-to-1 step-up transformer required to get the potential difference we needed to actually drive the film to play audio. On the lower right, you can see a picture of a film mounted into a sample holder inside of the sound isolation box. So here on the left, we have a closer look at a film mounted in a sample holder with the microphone sitting just in front of it. We placed the microphone as close to the film as possible. That way we could ensure that we were picking up only the sound that was passing through the film itself. In the upper right, you can see more closely the curvature on our sample holders. We were careful to calculate the optimal curvature that would give us the best output from the film. And then we made one holder that was roughly half that curvature, and then we also had one that was flat. So we had 3 different sample holders for 3 different testing setups. In the lower right, you can see a film mounted in one of the sample holders with the testing leads and the conductive tape we used to carefully apply the film to the sample holder to make sure we didn't have any shorts and got proper conductivity from the film to the leads.
So the whole purpose of these mounts and the tube and the soundproof chamber was to run full factorial experiments. 2 level 3-factor DOEs were run, 11 ones and 1 replicate per with averaging on the beta phase PVDF. We had 3 separate DOEs we ran, DC1, AC1, and AC2. Unfortunately, DC1 and AC1 proved inconclusive, but on the next slide we have AC2 results. And so as you can see here, we were able to prove proof of concept with sound canceling film with our DOE by attenuating sound at 0.5 decibels. Not the 5 that we had attempted to achieve, but proof of concept nonetheless. Additionally, curvature, thickness, and frequency all show as factors that are important in the outcome of the sound cancellation, as seen in the top left image. And the prediction profiler we used with JUMP was actually able to show us the most effective way to apply these conditions: high thickness, low frequency, high curvature. One thing we do have to mention about this data is that we do show a lack of fit present, meaning that our modeler had a large amount of error versus our actual data. But again, it does show the proof of concept that by using the piezoelectric film, we can in fact cancel noise. That brings us to our accomplishments and conclusions. So materials characterization, we chose PVDF piezoelectric film. It did the job. We had successful characterization and ITO deposition, demonstrating the piezoelectric beta phase has distinct properties from non-piezo alpha phase, which we did expect. Additionally, we successfully built test apparatus and collected data to perform our DOE analysis and prove that all interactions were significant. The product is not ready for market based on our current testing apparatus, but we believe with better apparatus and a better modeling system for sound attenuation, we could have a great product. Thank you for your time.